Oh, now the recording is started. So now recording is in progress. Today our class Thursday, 20th of January 2022. Tony volunteered in the previous part. The recording was not working to answer 3 questions. Tony, in a quick, please share your screen, answer the 3 questions for those who did not attend the class to benefit from your answers. Please answer them, then we can move to the next step.
Okay, yes, we'll do.
Start from the first question.
Yes, so the first question was, what is the cardinality of the Cartesian product A and B? So the formula is given. It will be just a cardinality of A multiplied by the cardinality of B. So in A, we could see there's 4 elements. So the cardinality will be 4. In B, there's 3 elements. So the cardinality will be 3. So therefore, it's 4 times 3. So the answer will be 12. Since 4 times 3 is 12. For the second question, is we're given the alphabet, and in this case is 0 and 1. To the exponent 0, it will just be empty, since we're not using any words or letters from the alphabet. So therefore, so that's just that. To the exponent 1, that means we're using 1 word from the alphabet. So in this case, we're either using 0 or either using 1. So therefore, it's 0, 1. So for the question alphabet, and we're given 2, so we could use 2 letters from the alphabet. So in this case, the answer would be 0, 0, 0, 1, 1, 0, and 1, 1. And clearing star is basically just a union of all possible words that could be formed by this alphabet. So it will just be like the union of this, with this, and so on. For the third question, the third question is about the empty string epsilon. The cardinality of the empty string, that would be 0. For the second question, what is 0 epsilon 1? That is just that basically is just multiplying by itself. So it will just be 0, 1. Since any element multiplied by epsilon would just be the number. So therefore, in the third case, it will be 0, 1 as well.
Okay, thank you, Tony. Please keep your slide. Okay, guys, there is a big difference between the cardinality of epsilon itself and the cardinality of the set that contain 1 element, which is epsilon. So the cardinality of set that contain 1 symbol, which is epsilon, it is 1. But in this slide that you are seeing right now, the cardinality of epsilon itself is 0. So we receive a question, but the recording was not on, from your colleague asking about this. Thank you for asking this question. So make sure that there is a big difference between the cardinality of element and the cardinality of set. Yes. So this is the cardinality of this set is 1, as your colleague is drawing, and the cardinality of epsilon itself as an element is 0, because it's empty set, empty string. So I hope those are all clear. Thank you, Tony. You can stop sharing your screen. We will start with handout 2 for will not go a lot with it. Let me share my screen. Can you see my screen right now, guys? with week 2, which is deterministic finite automata. We'll not start with the non-determinism. We'll start, thank you guys, those who answer yes. So we'll continue with deterministic finite automata that we started in the previous lecture. So you will have a new term, we call it regular language. What do we mean by regular language? Let A be a finite automaton, and let L be the set of all strings that are accepted by A. L, and it is denoted by L, which is the language, equal S as a string, accept S. We call L the language of A. Similarly, we say A recognizes L. So the first definition that we'll have today, which is the regular language. What do we mean by a regular language? A regular language, which is a language L, is called a regular language if there exists some finite automaton A that recognizes it, which means that will accept it. This is what we call a regular language. Strategies for creating DFAs. As I mentioned in yesterday class, sometimes you will see the DFA in front of you, and then you will be asked, is this automaton accept the following string or not? Like in yesterday examples in the class notes. And now we will also start getting some information that will allow us to design a finite DFA, deterministic finite automata. What are the strategies that we will use to create it? We will see in the few upcoming slides. Suppose I gave you an expression in a set builder notation or simply an English language description of a regular language and ask you to give the associated DFA. I give you a description in normal regular English language, or in your language or whatever language, and this description, how it will allow you to design the suitable deterministic finite automata that will represent this description. First, you have to start by writing out all possible state that you think that I will need them in my DFA, and assign them some kind of semantic meaning. Normally we call them Q naught for the beginning, Q1, Q2, Q3. Some of others will give them like a word that describe what they will do. All are accepted. Assign a start state and the final state or states. Sometimes based on the description I will give you, or in the future in your work you will be given, that you might hide different final state. How to think about it? Remember the if statement in the programming languages. Sometimes you'll have a final state if the condition is true or not. So at that time you'll have two final. Nested if, you will have multiple final states. Add in a transition to define the behavior. How I will move from this state to another state. What will transit me from this Q0 to Q1? What is the behavior that the program will take, or the statement or the language or the string will take to move me to the next state? This we call it a transition, and we use the delta for it. Simple. Example one. Example one. Give a deterministic finite automaton that accepts all strings with an odd number of zeros and an odd number of ones. So the description I gave you using the normal language, normal English language, that I need a DFA that will accept any string with odd number of zeros and odd number of ones. Now, to go to the first step, start by writing all the possible state that I might have. So when we are saying even number of zeros and even number of one, what are the possible states? Even number of zeros and even number of one, the one they ask for. This is the first one. Second one, even number of zeros and odd number of ones, or odd number of zeros and even number of ones, or odd number of zeros and odd number of ones. Based on the description I received, which one I should accept, or what is the accept state? Only this, because here they said and, not or. We have to be careful. So this is define the state. We said the step one, define the state. Those are the 4 states that I might have. So let's call, we said, and give them a name, either in numbers or like some kind of semantic meaning. What is the semantic meaning? I can take it even, EE, even odd, EO, odd even, OE, odd, OO. These are the name of the state. I'll not call them Q0, Q1, Q2. I'll give a semantic meaning based on the description I received from the question. EE is our start state, even. Since 0 is even, 0 is our accept state as per the question, which is odd. So this is the accept, this is the accept state, odd. I said before even, no. Based on the description, we will have odd, not even. So OO is our accept state. Now we'll go to step 2. Here we said the step 2, assign a start state and final states. So here, define a start state. If you haven't seen any zeros or one yet, which of our state would that correspond to? This is the answer of this question will show you the start state. We'll see now. Define final state. The question asks us to accept a string with even number of zeros and even number of one. Which our state does that correspond to? Here it should odd, right, guys? There is a typo within the handout. Fill in the arrows to define behavior. For each state, consider the scenario where you receive 0 as an input and 1 as an input, and then the transition to the appropriate state. So here we have even, odd, even, odd, even, and here we make 2 circles for the final states. So if I have 1, we will have even, odd. Then if we have 0, we'll have odd. If we have another 0, we'll go to here. So this is that consider all the state with the transition. Example 2. Suppose we modify the previous example to accept even number of zeros and even number of ones. So the EE will be the start state and the final state, and even number and odd number of zeros and odd number of ones. So here EE and OO would accept. So we'll have 2 final states. If this question came that this will accept even number of zeros and ones or odd number of zeros and ones. These are the case that we would accept. So here we'll have 2 final states. Can we reduce the amount of states in this question? But the best we can do are, we know, maybe using more states than we strictly need to. So normally in computing, we are trying to use the minimal resources, the minimal computation. to have an optimal answer. So if we can reduce the number of states, that would be perfect. So can we in this question reduce the number of states? Yes. How? We'll make it 2 state, even, even, or odd, odd, even, odd, or odd, even. So we minimize the number of states from 4 to 2. Exercise. Does there exist a set of transitions that will recognize our language? If so, fill in the transitions. So this is a homework for training purposes for you. Next class, I need a volunteer to answer this question. Okay. Example 3. Give a DFA, deterministic finite automata, that accept all strings that when interpreted as binary integer and are divisible by 4, which is, yesterday we talked about this example. So L, which is the language, has a string. This string equal T00, because we said any number divisible by 4 should end by 00. T belongs to the alphabet 0, 1 star. Using our strategy from before, define the state. What are the possible scenarios that we might end with 0, no zeros, end 1 0, or end with 2 zeros? If it's end of 1, which means end with no zeros. End of 1 0, or end with 2 zeros. Those are the 3 states that I might have. We also need to consider 2 special cases. If S equal epsilon, the empty string should not be accepted. 0 plus a string of 1 or more zeros should be accepted. So if I have 2 zeros and more, also should be accepted because it's end with 2 zeros. I don't mind what, if I have the last 2 digits are 2 zeros, whatever before it, I don't mind. We can handle these cases by adding an additional initial state. So it's initial state, a state end with no zeros, a state end with 1 0, and a state end with 4 zeros. Start state would be initial state that we talk about here. Define final state from the question, the one with end with 2 or more zeros. Fill in the arrows to define the behavior. So initial, if we receive 1, which means no zeros. However, we have ones, we will stay with no zeros. If we received 1 0, we'll go to stay 1 0, another 0 will go to 2 zeros. Here, if we receive 1 0 and the zeros are repeated, that means okay. Then if we receive a 1, we'll back to here. If we receive a 1 here, we'll back to no zeros. So this is our example. Okay. How about language of all strings that start with 2 zeros? So we'll accept any string that starts with 2 zeros, whatever the remaining. So here we have initial state, no zeros. If we receive a 0, there is 1 0. If we receive another 0, it will be 2 zeros. Whatever repeated again, 0 or 1, I don't mind. If I receive a 0, then I receive a 1, we'll go to dead end, whatever 0 or 1, because it's not started with 2 zeros. And if I receive 1 from the beginning, I'll go to the dead state. In this example, we have something we call it dead state. If we talk about the beginning of the string and the condition is not satisfied, that means we go to dead state from the beginning, whatever the remaining element of the string. Questions still here? Okay.
Hi, sir. I just had a question.
Go ahead.
in DFA example 3, could you just clarify like what the states are exactly and why like 2 zeros alone is the sort of final state?
Yeah, because they said in the beginning that any string are as a binary number are divisible by 4. And from yesterday class, we said that any binary string that end with 2 zeros, 0, 0 at the right side of the string, it is divisible by 4.
Oh, okay, I see. I think I was just confused as to like.
Yeah, so it's following to our yesterday example.
Okay, sounds good. Thanks.
Yeah. Okay. So in example 4, we saw that the did state is a state that cannot ever lead to an accepting state. So if we see here in the did state, whenever we arrive to it, however the program is continued or the string is continued, it will not lead us to the accepting state. So we can make it start no zeros, 0, 1, 0, 0, 1. So we can set no zeros, we can stay at the initial state and that's it. No need. So here we reduce one state that is not needed, which is the did state. So here, if I ask you to give a DFA that accepts all string containing the string 11010, wherever this string can be. So here we can start. These are simple questions. We can start straightforward without naming the state, without doing anything. So start 11010, wherever, whatever before the start and whatever after the start. So in this question, it's a straightforward, just draw it and move each one to be a transition state, and that's it. So fill in the other arrows, paying attention to the most recent seen characters. If we will see the other character, here is 1, what if we have 0, here is 1, what we have. So here we can do, if we have 0 at the beginning, it will keep repeating. Once we receive 1 and we have 0, we'll back to the initial state. If we have 1, 1, then we receive 1, we will stay here till we receive a 0, then we will continue. So the last 2 ones will complete the string, and all of these arrows and all other states, whatever we have. To study, to be the like this string to be at any part of the string. So these are the DFA that represent this to be a partial. This is an example of a string matching searching. You took in programming the search to search for certain element or for certain string or for certain word in a dictionary. So these DFA represent these basic computing steps, which an important application of finite automata. The strategy is to use state to represent progress. The work comes in figuring out how far back you have to go on a particular mismatch. And here, if you wanted to read more about this, go to Morris Pratt algorithm. If you click on it, you will read about it in Wikipedia. Algorithm can generate these kind of DFAs in an amount of time that grows linearly in a number of state alphabet. How much state I have, then the complexity will be grown in the string, or how many states I'll have more than the complexity of the program will be grown. And here the 6th example. What if we ask to give a DFA that accepts all strings containing the reverse of this one? So we will start from the end and we end at the initial state of this example. We'll move it. We would make the starting state the accept state and the vice versa, reverse the arrow direction of the previous question. At first glance, this change wouldn't seem to make sense. Some states have more than one arrow coming out of them with the same symbol. For example, if you receive a 0 in the start state, which state should you transition to? Or could you maybe somehow take both at the same time? So next class, we will have the class note of this part with more example that we'll solve in the class. And then we will start with the non-determinism. Any question for today? It's now 1:20. So the 10-minute breaks, I keep it at the end of the class. So if you have any question, please go ahead. Otherwise, you can leave and see you next Wednesday, guys. Thank you, Vern. Thank you, Mahira. Thank you, Tomofi. Yeah, it will be tomorrow or late tonight, both classes. Thank you, Abdullah. Thank you, Brandon. Have a nice weekend, guys. Zachary, Alex, Zohair, Connor, Ryan. Thank you. Which question will be volunteer question for next class? The question in slide, let me see. In slide 9, the exercise in slide 9. Okay, Ryan. Faris, thank you. Alex, Connor, Ryan, Tayi, Dana, Rashid, Diffu, Taiju, you have to. Tara, Megan, do you have any question or shall I stop recording? Okay, T, ask your question. Yes, the final state is the state that would accept the string. Yes. Rashid, Connor, Dana, do you have any question? Connor, for the DFA example 1, you use the start state as EE. Could you choose the start state to be OO? If you answer the exercise, you will know the answer, Connor. So I leave it till next class with the exercise answer. Why we start with EE. So the exercise in slide 9. Okay. Rashid or Rashid, Defo, Dana, Connor. Okay, I'll stop recording. Have a nice weekend, guys, and see you next week. Bye.